Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today we have Efstratios Tsoukanis, who is a PhD student at the University of Maryland. We are happy to have him here today to tell us about Coorbit Invariant Embeddings. Take it away, Efstratios.
Hey everyone, thank you, Emily, for the introduction. So today I will present our joint work with my advisor, Professor Radu Balan, and as the title says, I will talk about invariant embeddings. Before I state the result, let me first try to convince you why these results are important and interesting. So, suppose we're doing a medical survey and we're having some patients and we are examining them, doing some medical tests. For example, here I have put cholesterol, vitamin B12, and vitamin C. Our patients are George, Liam, Nicholas, and Sophia. And we want to use this data in a neural network, for example. So it makes sense to represent this data as a 4x3 matrix that its entries are exactly this number for cholesterol, vitamin B12, and vitamin C. Now imagine that here I put the name in alphabetical order. Imagine instead of putting the names in alphabetical order, we just put it in the order that we call this person for their medical exams. Then, for example, first we call George, then we call Sophia, then Liam, and last Nicholas. We'll have a completely different matrix, but it makes sense that for any prediction model, we want to give us exactly the same result if we feed it with these two matrices. So we want to create a model that takes in as input matrices and it is invariant under any possible row permutation. Because we don't want to have different results. So another similar example comes from chemical engineering, where we want to examine some chemical compounds to see if they're toxic or not. Chemical compounds look like this, so it makes sense to represent them as a graph, and so use the graph adjacency matrices to do machine learning. Of course, again, when we want to examine if a chemical compound is toxic or not, we don't care about the labeling of the nodes. So we don't want any possible relabeling of the nodes to change our result. For example, here we have these two graphs that their adjacent matrices will be completely different because I have relabel every node. But as you can see, it's exactly the same molecule, the same chemical compound. So we want to give exactly the same result. So in this case, we have a matrix again as an input, and we want, if we perform any permutation of the rows of the matrix and then exactly the same permutation on the columns of the matrix, to have again the same result. We don't want to have any difference. So this is another example that we have a symmetry and we want our model to be invariant under that symmetry. Here is both rows and columns permutation. In the previous example, it was just row permutations. So now we have two different approaches on how to construct such a, let's say, symmetric functions. The first idea is called data commutation, and it is to add the whole orbit. So have our data points, and for each data point we have, add its whole orbit to data set, and then use the whole orbit to feed the neural network. This is like the most straightforward method, and will have good result, but it's too computationally expensive to create such a highly symmetric function. So we also try to have some other ideas. And another idea is, instead of using our data space, to use the orbit space. So have its orbit as one point. So take actually the quotient space with respect to the symmetry we want to preserve. The problem here, of course, is that when we feed the neural network, we cannot feed it with orbits or elements of quotient space. We want to feed it with elements of an Euclidean space. So in order to solve this problem, our idea was just to embed our quotient space to an Euclidean space, and then use this target space as our data space for our model, for training our model. So the topic I will talk today, it's kind of similar with Daniel Packer talk last week, because I try to embed quotient space to some Euclidean space. So in order to create such embedding, the most natural thing for me, at least, is to create a map from our original data space to the target space, that this map will be invariant under the symmetry we want to preserve, and then do a natural lifting of this map to the quotient space. So we want to create a map that it's invariant under the symmetry, any symmetry we want to preserve. Now let's see some bad examples of such embeddings. Suppose that we create well-defined embedding from the quotient space to some target space, but it takes two different orbits and send them to the same point. We don't like, actually, we really don't like this, and the reason is that any model that we're training on this target space will treat the orbit x hat and y hat here as to be exactly the same point, so we'll give always exactly the same result. And I guess we don't want to have, for example, in the medical survey example, to have some completely different medical tests and then always have them giving the same result. So we want our embedding to be injective on the quotient space. Another thing that it is not so good is having two orbits that are really close to each other, and then our embedding send these two orbits in points that they're far away. Again, the reason we don't like that is that when we have very similar results in our data, we want also to have similar model prediction. So we want also our embedding to have an upper elliptic bound, and of course to have also a lower elliptic bound. We don't want to have two orbits that are far, far away and then send them almost the same point, because probably then we have very similar predictions. So it will be like similar problem when in the with the case that our embedding is not injective. So these are the properties that our embedding want to have. So now let's try to formulate our problem. So given a finite orthogonal group acting on a vector space V that you can imagine always to be RD, we're going to construct a map phi from V to some Euclidean space Rm, that it is also good n to be as small as possible, such that f of gx, phi of gx is equal, here should be also capital phi, sorry. So phi of gx should be equal with phi of x for every group element. The reason we want that is in order to be able to lift our embedding and be well defined the quotient space. So with a slightly abusive notation, from now on, when I talk about our map phi, I always mean about the map defining on the quotient space V hat with respect to the group action. And we want phi to be injective on the quotient space, because we don't want like the bad example one we had in the previous slide. And also we want phi to be bi-Lipschitz on the quotient space. Here, of course, in order to talk about stability, we have to define a distance in the quotient space. And like a natural way to define distance is to say, okay, the distance of two orbits, it's the minimum distance of any possible pair of points that belongs to the two orbits. So this is like our general problem. Any questions until now? Okay. So now we have separate this problem in 4 different projects. The injectivity problem, that is construct injective embedding from our quotient space to some Euclidean space. The stability problem, that is obtained by Lipschitz bounds of this map. The recovery problem, that is we want to, if we're able to inverse the embedding phi, and also we want to analyze some like very popular application, for example, for graph theory. That's a very hot topic. I have crossed out the recovery problem, the specific applications, because I'm not going to talk about them today at all. So you can just have in mind the injectivity problem and the stability problem. And I will mainly talk about the stability problem, because for this we have already have some results. But also I have to talk about the injectivity problem, because we need that in order to talk about stability one. So sorry. So now let's see some already famous results in this problem. So suppose that for any vector W, we define a map PW from our vector space to R. Then we say that PW strongly separates orbit in our space if and only the set of vectors W that for fixed x and y that are non-equivalent elements, the set of W that such that PW fails to separate x and y has algebraic dimension at most d-1. And then we say PW strongly separates orbits. And Nadav and Goldler showed that actually we just need 2 times the dimension of our space plus 1 generic vectors W1 to W2D plus 1 in order to solve the injectivity problem. And this is a very interesting result, because we see that the number of vectors we need does not depend only on the dimension of the space. It's 2 times the dimension plus 1. And it does not depend, for example, in the cardinality of the group. And that's good, because cardinality of the group be big, for example, like n factorial or d factorial. So this is like the target space. It's, let's say, low dimensional. Its dimension is like approximate 2 times the dimensional of V. And A specific example of such a strongly separating map is the max filter that was introduced by Cahill, Iverson, Mixon, and Packer. So for fixed vector W, the max filter is a map from V to R that takes a vector X and then calculates all possible G acting on W inner product with X for all G in our group, and then calculates the maximum element of this set. And this is the max filter. And actually, in the theorem, they showed that for 2D, where D again is the dimension of our space vectors, generic vectors with respect to the max filter solves the injectivity problem. Notice now that here we have just 2D vectors, while before we had 2D plus 1. The reason that we were able to get rid of an additional dimension is that because of homogeneity reasons, it is enough to be able to separate all non-equivalent x and y such that, for example, norm of x is equal to 1. So instead like of having to do with something that has dimension 2D, that it's all possible pairs of x and y, we have something that has dimension 2D minus 1, because we have fixed the norm of x or the norm of y, for example. Now for the stability problem, as like state-of-art result, I like search, like actually I see that last week for the first time, states that for the max filter, if we have at least P of G times D minus 1 generic vectors, where this P of G is the Voronoi characteristic of the group, then we're guaranteed that we have that phi of x is by Lipschitz, so it has also a strictly positive lower Lipschitz bound. So now let's pass to our results. So before we state our result, let's first talk a little about Coorbit. So when we have a vector space V and a group G acting on V, the orbit of an element X of V is just all the possible vectors G of X. So the Coorbit is something very similar, but we don't have just the Coorbit of a vector X. We have a Coorbit of the vector X with respect to another vector. And again, we just take all the possible inner products G acting on W with X. And this set is the Coorbit of X with respect to W. So for example, we see that the max filter we introduced before, it's actually the maximum element of a Coorbit. And like two very popular like transform that use this Coorbit theory that I will just state, it's a wavelet transform. It's like, and the short time Fourier transform. Like they're very popular in time frequencies analysis. And as we can see, like the wavelet transform takes a kernel and slides it through our data, while the short time Fourier transform cuts some data and perform Fourier transform in this like segment. Also, as you can see here, we have like some continuous group. So it's kind of different examples for our, because we only assume that we have a finite group G. So this is like continuous Coorbits. Here in our results, we have always just finite Coorbits. So now let's see our proposal. So let a finite subgroup of orthogonal group with cardinality capital N acting on RD. Then for a number P, we fix some windows W1 to WP and a subset S of capital N times P, where this subset has cardinality N. We also define the truncate function that just take a vector and sort it in decreasing order. So now, for any I in P and J in capital N, we define the map phi of ij from our space to R, from V to R, where Pij takes Pij of x, takes the Coorbit of x with respect to vector Wi, sorted in decreasing order, and then take the jth component of this decreasing in ordered Coorbit. So now for S, where S is recall a subset of capital N times P and the window W1 to WP, phi of Ws of x, take the f of the phi of ij for each I, j in subset S. So because it's kind of confusing, let me try to visualize it. So for example, the max filter, that is a special case of our proposal, have as S just the first element of each column. So because we take the Coorbit, for example, for W1, we sort it and we take just the first element. We take the Coorbit of W2, we sort it, we take the first element. And what we want to see is what happens if we don't take just this first orbit, but any arbitrary subset of this set of subset of capital N times P. So a result we had that it can be seen like very similar to the max filter result, is that actually we don't, if we have at least 2D vectors with generic vectors with respect to Lebesgue measure, we don't need to take just the max filter. We can take any element for each column of capital N times P. For example, here, if we take the second greatest from first column, the third from second, the max filter from third, the mean filter for fourth, and so on. Again, we solve the injectivity problem. So in order to solve the injectivity problem, it is not required to take always the max filter. You can take anything you want from each column. This result, it's like really easy to prove. And if someone translate our notation, in our notation, the max filter theorem, it will be just a corollary, for example. It is not like any very different idea. But of course, we don't want to just play with 2D different columns. We want to see if by using more elements per column, it is possible to reduce the number of windows you need in order to solve the injectivity problem. So to see if we can use less than 2D windows. And we don't have any result yet for this problem, but we believe that given a specific S, the number of windows you need in order to solve the injectivity problem, so the number of generic vectors you need, depends on the spectral properties of our group that act in our vector space. And the way we try to solve this problem is by calculating the number of p tuples of vectors w1 to wp that fail to separate different orders, different orbits, sorry, and we're going to show that this set has Lebesgue measure 0. And the way to do is like we try to describe in a simple way this set. So we see that it is here we have a finite union, and then we have like a continuous union, where here gamma is the set of all possible non-equivalent pair of vectors. And we want to show that for any fixed pi1 through pi p and sigma 1 through sigma p, this union has 0 measure in VP. And the way to do that is we try to create a partition of non-equivalent pairs gamma on a bad set gamma 1 and on a good set gamma 2, and then use the lift and project technique separately on gamma 1 and gamma 2. Let's also see what lift and project technique is. So suppose that you want to calculate the measure of a set A that has this form, where it's a union under a smooth manifold, and its Sx is a linear space. Then a way to do is to express this as a vector bundle or a finite union of vector bundles, and then take the total space, project it in the second component, and compute the measure of the projection of the total space in the second component. So I think with this method, almost all the previous results we saw like use this method of lift and project. So now let's pass to the stability problem. The reason I talk about the injectivity, even though we don't have any result yet, is because our stability result actually used the injectivity. So it makes sense to talk about the injectivity first. So if I had to state, like, to give a title of this talk with 3 words, will be just injectivity implies stability. And this is like our main theorem, states that any possible proposal of embedding of this form of like subset of Coorbits, that it is injective on the quotient space, then it is also bi-Lipschitz in the quotient space. And the corollary of this result is that the max filter, because it is a special case of our approach, also when it is injective, it is also bi-Lipschitz. So let's try to see the proof for the upper and the lower Lipschitz bound. So as usual, the upper Lipschitz bound, it's much easier, and we also have a formula. Here you see the square root of b, where b is this like ugly formula, is exactly the upper constant of upper Lipschitz constant for our map phi of ws. And let's see a summary of the proof. So recall phi of ij, that we just take the jth component of Coorbit of x with respect to wi after we have sorted in decreasing order. And from a fundamental theorem of calculus, we have that fij of x minus fij of y is equal this integral. And now we will always take the worst case scenario. So here we have this g of jt, where this element can change a finite number of times as t runs from 0 to 1. And so if we take for fixed I, the whole subset of Coorbit of Y of I that we use in our embedding, we have, excuse me, that the norm of this subset of Coorbit is exactly the sum of these integrals. So we can pass it to the integral of the sums. And now we see here we have y minus x inner product with this kind of vectors. So now the worst case scenario is if we find the for all possible choices of these group elements, the one that makes the matrix G of JWI as J runs to have the largest eigenvalue, and then y minus x to be exactly eigenvector for this eigenvalue. So this is what this formula BI represent. And then in order to, because here is the norm of just the difference of two subsets of Coorbits for one window, so for a fixed I, but because we have a lot of windows, we just add in when we want to find exactly the distance of the two of the embeddings of X and Y, we just add the sum from I from 1 to P, and we have exactly this sum of BI, which is our upper elliptic bound for the map, because you see that it's less or equal than this B, which is exactly the sum of BI times the square of the distance of X and Y. So this is the formula for the upper elliptic bound. And I found interesting that we use the fundamental theorem of calculus because I haven't used it a lot of times. And this could also be solved just with a combinatorial argument, but it will take 3 pages, and this it take half page. So it was really nice to be able to use such a fundamental theorem for a real life problem. So now let's go to the proof for the lower elliptic bound, that it was much harder. Here, because this proof was very technical, I will not give I will just give a brief summary of how we work to prove that. So here, as I said before, we didn't provide any formula. We just showed that it is impossible if phi is injective to have a lower elliptic bound 0. So in our first step, we showed that if the lower elliptic constant vanishes for our bending phi of WS, then it also vanishes locally. That means that we can find two sequences, xn and yn, that converge to each other, and for these two sequences, the elliptic bound is 0. And this then we can also scale xn and yn. So for example, we can always assume that we say, okay, we just always decide that the norm of xn to be 1 and yn to have norm less or equal than xn. If this is not the case, we just interchange xn and yn. And so because xn has always norm 1 and converges to a point z1, then also the norm of z1 will be exactly 1. So first we localize our problem, then we scale it so we're in a compact set. And then we can also align with respect to the quotient distance. So we can always assume that actually the norm xn minus yn is exactly the distance of xn yn. The norm of xn minus z1, that it's their common limit, it's exactly the distance of xn and z1, and the norm of yn and z1 is also, again, exactly the distance of yn and z1 in the quotient space. So now we have both localize and align our sequences, and then by using this z1, we're able inductively to construct a sequences of vectors z2 through zk, such that each vector, it's much smaller than the previous one. So it's like, imagine like a nested sequences of vectors, such that the dimension of span of z1 through zk is always k, so they're all linearly independent. And we also were able to show that the lower Lipschitz constant vanishes locally in a convex set of this form, sum from r equal 1 to k, ar zr, where ar is very close to 1. But when I say that lower Lipschitz constant vanishes locally, I mean that, excuse me again, for any point of this convex box, we can find two sequences that converge to that point and achieve lower Lipschitz constant to be 0 for our map phi of ws. And now the next step was continuous inductive construction until k reach the dimension of our space. So now again, we have a non-empty convex box of this form, sum of from r equal 1 to k ar zr, where r is very close to 1, where again the local lower Lipschitz constant vanishes. But now recall from previous slide that the vectors z1 to zk are always linearly dependent. So now that means that actually this convex box is an open set in our space. So that means that we have an open set, and in any point, for any point of this open set, we can find two sequences that converge to this point, and their lower Lipschitz constant vanishes. And then if you have this property, it is easy like to construct a contradiction with injectivity hypothesis, because remember that our original theorem stated that injectivity implies stability. So what we said was like, okay, suppose that we have injectivity and we don't have stability. And what we did was that we constructed two sequences of vectors, two vectors, sorry, that it was constructed by small perturbation of the center of this convex box, x and y, such that x it's non-equivalent to y, but phi of ws of x is equal with phi of ws of y, and that contradicts the injectivity hypothesis. So that means that our theorem like is proved, and actually just yesterday we uploaded on archive this result. So like it's very new. So yeah, this is our main result, and that I want to talk about today. And like now for future problems, the two problems that I don't know if they're already solved, but I find them interesting, is first, find a formula for estimating the lower Lipschitz bound for phi of ws, because we showed that injectivity implies stability, but we didn't provide any formula for the lower Lipschitz bound. and this is what we want. There are some results by Dustin Nixon that I know about the formula for low ellipse bound, but I think they require more windows. They don't require just injectivity. They require a specific number of windows. And another future problem is to solve the injectivity problem, but for generic vectors, generic windows with respect to Zariski topology, because all our result and also the other result I know, in the injectivity problem, they state that, for example, 2D windows, generic windows with respect to Lebesgue measure solve injectivity problems, but we suspect that probably also, for example, 2D generic vectors with respect to Zariski topology solve the injectivity problem. So I think also that's an interesting thing to work on. So yeah, this is the paper I referred during the talk. And thank you very much. Do you have any questions?
All right, let's thank the speaker.